Did you have nice weekend? The flowers are very good here in Kaist. I spent about 2 hours yesterday with my wife in Kaist. Not for study, just looking around. Today's topic is fire and explosion. I think most of you are familiar with the fire, not with explosion. Explosion is very rare in our daily life, but every day we are in touch with the fire. So as you know, we need 3 components for fire or explosion. First is oxidizer, like oxygen, F2 or Cl2. But oxygen is practically the main player of oxidizer. Second component is flammable material, like methane, LPG, LNG. And the third one is ignition source. So we need all of them to have fire or explosion. If one of them is missing, we cannot have fire or explosion. So as you know, it's very hard to remove or separate ignition source from oxygen or fuel. So the typical approach to removing fire or explosion is to separate oxygen and fuel. So we will talk about the characteristics of ignition sources later. Do you know MSDS? If you are supposed to handle with hazardous material, you are given a sheet, data sheet. The name of the data sheet is Material Safety Data Sheet. There are many instructions and the data concerning the safety in handling the material. And if you read carefully the MSDS, you can find many numbers concerning the fire and explosion properties. I excerpt some of them from MSDS for methane. Here are the terms and the numbers. First, appearance. Methane is colorless and odorless, but we can smell when we have a natural gas leak in our kitchen, because the coke gas put some special chemicals into their gas. Okay, so but natural gas itself has no smell. Explosion limit, LEL, UEL are 5%, 15%. Flash point minus 121, melting point, boiling point, auto ignition temperature, density, water solubilities. These are the typical properties that are given in MSDS. Let's check one by one. First, flash point. What is flash point? By definition, flash point is the lowest temperature at which a flammable liquid gives off enough vapor to form an ignitable mixture with air. Here we have methane, liquid methane. LNG can be a kind of approximate material to mixture of whose major component is methane. We have LNG here, and it will give up some vapor. Okay, so if we increase the temperature of this LNG, the vapor composition here, vapor pressure will increase with the temperature. So if we give a spark to this mixture, it will, we can have a flame. That temperature is flash point. So the flash point is minus 221. Below that temperature, even though we put some flame, the flame cannot sustain. The flame will disappear because the vapor pressure is not enough to sustain the flame. Interesting point is the melting point. Melting point is around minus 182. You know boiling point. Boiling point is the temperature at which the methane can boil, like the water at 100 Celsius on the atmospheric pressure. So the temperature, the melting point is just 20 degrees lower than the boiling temperature in case of methane. So minus 221 means that LNG is not LNG, it's a solid, like ice. Okay, ice, and it's a solid methane, and the solid gives off some vapor, but the flash point is minus 221. That means above that temperature, if we give some spark or flame, the flame can sustain. Fire point, the lowest temperature at which it will continue to burn after ignition for at least 5 seconds. That means if we give us a spark, the flame can sustain. So the flash point and the fire point is a little different. Flammable liquid. Do you know NFPA? Maybe National Fire Protection Association. National means United States. United States standard, because NFPA is very good reference. So many companies and countries consider it a kind of international standard. So liquid with a flash point 38 means the temperature of human body. Okay, so if the flash point is less than the human body temperature, the liquid, the material, gas or vapor, the material is called flammable liquid. Combustible liquid means that the flash point is greater than the human body temperature. So the flammable liquid is easier to ignite than the combustible liquid. Flammable explosive limit is the range of concentration that can lead to fire or explosion. So UFL is an acronym for upper flammable limit. LFL is a lower flammable limit. UEL is just for the concentration for explosion. So UEL is equal to UFL. Fire and explosion are basically the same phenomena, except for their speed. So UEL is equal to UFL, LEL is equal to LFL. So here we have two values. One is LEL is 5%, UEL is 15%. That means if the methane concentration greater than 15%, we cannot ignite the mixture because of lack of oxygen. Okay, in order to have a fire or explosion, we need enough methane. At the same time, we need enough oxygen. So if one component is dominating over the other component, methane is much more than oxygen, we cannot ignite the mixture of methane and oxygen. If the methane concentration less than 5%, the mixture is too lean in terms of fuel, so we cannot ignite the mixture. Can you understand me? You can understand at this point 5%. Methane concentration is too low. We don't have enough fuel. If the methane concentration greater than 50%, the concentration of oxygen is too low, so we cannot ignite the flame. If this room has 50% of methane, and even though we try to ignite the vapor in this room, nothing happens because the concentration of oxygen is too low. So assume that we have liquid containment here. By accident, we have a small hole, then the liquid will erupt from the containment. Because of the pressure difference, the erupted liquid jet will disperse as small droplet like this. So assuming this situation, the jet will be atomized into small fine particles, and the fine particles will evaporate due to its high surface area. It has substantial surface area, so the liquid can evaporate very easily. The vapor fraction here is proportional to the vapor pressure of this liquid, okay? But the vapor pressure itself is a function of temperature. The vapor pressure is proportional to the temperature of the liquid. Can you understand me? No? Every liquid has vapor pressure as a function of its temperature. Is it correct? We have water here. Today I don't bring any cup of coffee. Assume that we have a cup of water. The water temperature, for example, 20 degrees Celsius. then this water will generate vapor, whose pressure is governed by the temperature of this liquid. So how much is it? If 20 degrees Celsius, it's around maybe 0.1 bar. You are giving me a very strange look. Okay. We have a water here, and we use a vacuum. Okay, like this. Nothing is here. We have a cylinder, and we have a vacuum pump here. If we pump up the air inside, we can keep a very low vacuum. For example, 10 to minus 3 bar. How about we have a water here? 20 degrees Celsius water. Even though we pump up all the air inside, the liquid is supposed to should gives off some vapor. So the water vapor will take place here, and the pressure is 0.1 bar. I don't know the precise value, but so what I mean is that the vapor pressure is proportional to the liquid temperature. If we increase the water temperature, the vapor pressure will increase accordingly. When the water temperature is 100 Celsius, what happens? Yeah, the vapor pressure is equal to the atmospheric pressure, and we can observe the bubbling phenomena. So bubbling is just coincidence where the atmospheric pressure is equal to the vapor pressure of the liquid. So we can make the water can boil at 20 degrees. Okay? If we use a vacuum pump and if we keep the pressure here 0.1 bar, then we can observe the boiling of liquid. Arlene, can you understand me? Okay, now the Korean guys are, I need to check the Korean guys. 무슨 말인지 알겠어요? 그렇죠. 리퀴드는 어떤 상황에서든지 자기 온도에 맞는 베이퍼 프레셔를 항상 줘요. 자기 온도에 맞는 베이퍼를 항상 위로 내보내는 거죠. 응? 그렇죠. 얼음이 있다. 얼음이면 어떻게 돼요? 얼음도 마찬가지예요. 그게 압력이 낮을 뿐이지 항상 액체든 고체든 자기 위에 뭔가 비어있으면 어떻게 해요? 자신의 일부분을 보내죠, 그쪽으로. 보내서 이제 자신의 일부분을 보내. 그다음 베이퍼는 어떻게 해요? 자신의 일부분을 리퀴드로 보내요, 자꾸. 분자 상태로 생각하면 분자들이 마음대로 움직이잖아요. 그래서 리퀴드도 막 분자가 자기의 템퍼러처에 맞는 운동을 하면서 계속 튀어나가려고 그러고, 베이퍼 쪽에서는 걔도 아무데나 튀어나가면서 또 일부분 리퀴드로 들어가겠죠. 그 두 개가 딱 밸런스를 이루는 게 뭐예요? 그게 베이퍼 프레셔죠, 단순히. 처음 듣는 얘기인 것처럼 표정을 짓고 있어서 내가 지금 이해하고 계신지 이해했죠? 그래서 if you check the internet and the vapor pressure of water, then you can find a curve like this. Okay? This is just vapor pressure of some liquid. This is the temperature. Typically, the curve is nonlinear, exponentially increasing with the temperature. Not like this, like this. So this is the partial pressure, vapor pressure or partial pressure. So at 1 bar, this, because there are some oxygen or nitrogen here, we can convert the vapor pressure into concentration. So at 1 bar, the concentration has the same meaning of vapor pressure. What I mean is that if we open the cap of this cup, and because the vapor pressure of water at 20 degrees Celsius is 1 bar, 0.1 bar, what is the concentration of water here? 10%, because 1 bar is our atmospheric pressure, and the water should have 0.1 bar. That means 10% of this atmosphere is water. What is this? This is the absolute humidity. 절대 습도죠, 이게 절대 습도. Absolute humidity. What is the relative humidity? Ratio to the absolute saturated pressure. Okay. So this axis can be interpreted as vapor pressure. So if you have any question about this phenomena, please approach me, and I can explain. Stoichiometric composition. Stoichiometric composition is the ideal composition. So that we can have no reactant left. Reactant means the oxygen and the fuel. We don't have any reactant remaining after the reaction. This is the stoichiometric concentration. If we have hydrogen mixed with water to form water, right? So if we react like this, we may have some hydrogen left. So the stoichiometric concentration is like this. Sorry. Stoichiometric concentration is like this. This is the stoichiometric concentration. In Korean, 등량? 뭐라 그러죠? 등량비. 등량. Anyway, I think you can understand what the stoichiometric concentration is. Most materials start to burn at 50% of the stoichiometric concentration. What I mean is, let me make myself in this example. We are trying to burn heptane. Heptane is C7H16 plus 11O2 leads to 7 CO2 plus 8 water. This is the stoichiometric concentration because we don't have any heptane and oxygen after the reaction. The stoichiometric mole ratio, the ratio of heptane to oxygen is like this: 1, 11. 11 oxygen always have 11 times 4 nitrogen if we burn the heptane in air. So the concentration of heptane is 1.8. So 1.8% is a stoichiometric concentration. If we have here we have heptane 1.8%, and if we burn the heptane, we have only CO2 and H2O and nitrogen here. No oxygen and no heptane here. At 50% of the stoichiometric concentration, that means 0.9%. But the experimental value is just 1.1. So what I mean is, what is 1.1? This is the LEL, LFL, lower flammable limit. Okay? Most models started to burn. Started to burn means it's LEL, low explosion limit or low flammable limit. 1 volume percent means 1 volume percent means 100 bar, 0.01 bar. So this vapor pressure corresponds to the liquid temperature of -5 degrees Celsius. The experimental flash point is around -4 degrees Celsius. So even though you can find the LEL or flash point in the data book, you can have a kind of feeling about how much, what is the flash point or the LEL of the material through this kind of reasoning. Let's think about the flammable limits. The flammable limits, the LFL, LEL, or LEL and UEL should change with temperature, pressure, and the presence of inert gas. So basically, let's think about the fire or explosion phenomena. Fire and explosion is a gas phase reaction. Do you agree? So even though we have LNG here, if we put the flame into the LNG, nothing happens because we don't have enough vaporized component here. So we cannot ignite liquid over solid. We can ignite the material only after the liquid and solid vaporize. I think most of you have a good experience having a campfire with some wood, logs. So that's the solid. 장작. We have a campfire with solid wood. What happens? The solid decomposed into gas. The gas is burned, okay? Not the solid itself. we have a coal, but if the coal is solid, we cannot burn it. The coal should turn into gas, and we can burn the gas, the vapor. So fire and explosion is gas phase reaction. So typically, the fuel form a radical. What is a radical? Do you know ion? Ion? Ion. Do you know ion? Salt is NaCl. If we put the salt into water, the salt is decomposed into sodium and chloride, but they exchange on electron. Okay, so one electron from nitrogen moves to chloride molecule, and we have ion. This is the ion. Ion is unbalanced electrons. What is radical? This is electron. Okay. This state is called radical. Okay, a molecule with free electron, but the net charge is 0. This is radical. So we cannot stabilize radical because they are very active. So during fire and explosion, we have radicals. For example, we have CH4. And during the reaction, we have this kind of material. Some methane with a free electron. This thing is called radical. The radical is very reactive. So it reacts with oxygen to generate more radicals. So the radical reacts with oxygen to form CO2 and water and radicals. So it generates one radical, generates more radicals. Then we have a kind of chain reaction. So radical generate radical, as well as CO2 and water. So the speed of reaction is increased. So considering this kind of mechanism, the chain reaction, fire and explosion, is affected by temperature. Temperature is level of internal energy of the molecules. So if the temperature is high, it means the energy state of the reactant is high. So they are more ready to react with each other. So if the temperature high, the reaction rate is high. We are more easy to ignite the mixture. Pressure. Do you remember the gas dynamics theory? When you are sophomore or freshman, you may learn about the model of gas, like the tennis ball. No? The typical model for gas is the hard tennis ball, perfectly elastic balls. They can move freely, and they can collide with the others. So this is the model of gas. What is the name of the theory? So the high pressure means that the distance between two gas molecules is closed. And the high pressure means high density of gas. So the distance between two molecules, and the distance between oxygen and the methane is reduced. So they can react easily, more easier than in low pressure. How about inert gas? Inert gas play nothing, but they take the space. So they can collide with radicals, or they can block the movement of the oxygen or radicals. So they are kind of barrier to propagation of the reaction. So LEL, this is the lower limit concentration for fire or explosion. If we increase the temperature, LEL decreases. That means they are more activated and they are easier to ignite. We can ignite them at lower concentration if the temperature is higher. LEL decreases with the pressure. In the same way, we can ignite more easily the mixture at higher pressure than in lower pressure. Do you agree with me?
The previous diagram, the area is decreased with the pressure in the time.
Yeah, LEL is decreased with pressure.
How about
UEL, it is upper limit. So LEL and UEL are confusing sometimes, but think about just that if we increase the pressure, that means the mixture of oxygen and methane are easier to burn, right? So that means the concentration, ignitable concentration region should be increased. Okay, so LEL should be decreased and UEL should be increased. So with the temperature, the flammable region increases. Okay, LEL decreases and UFL increases. So we have this curve. What is this curve? This is saturated vapor pressure curve or liquid vapor equilibrium curve. Vapor pressure is just result of vapor equilibrium. Okay? And this is a flash point. And the LFL or LEL decrease with temperature. UFL or UEL increases with temperature. So at higher temperature, the the ignitable region is wider than that in lower temperature. Is it consistent with your insight? Minimum ignition energy. If we have a mixture, we insert some spark, then we have a fire. But there is a kind of limit, lowest limit of for the spark to have. The lowest energy of the spark, the ignition source, is called the minimum ignition energy. It depends on temperature, percent of combustible, time of a compound, blah blah. But important thing is this curve. It has some dependence, but take a look at the unit of the energy, minimum energy. It's millijoule. What is millijoule? 1/1000th of joule, 0.001 joule. Okay, so it's very small. If I drop this one, how much energy I can have? It may be 50 grams. We have, if I drop 1 meter, the potential energy is, that means times, how much is it? 10, about 0.5 joule. That means 500 millijoule. Okay? The other minimum ignition energy is just 1 millijoule. So 500 times greater than the minimum energy. So anything can cause spark. The spark from rotating machine, spark caused by drop object, like this. Electrostatic sparks caused by operators, like this. This kind of action can cause 20 sparks that are enough to ignite their mixture. So conclusion is that it's really impossible to remove all the ignition sources. We can decrease the population density of ignition sources, but it's very hard to remove all the ignition sources completely. Auto-ignition temperature. Auto-ignition temperature is that the vapor, the mixture of oxygen and methane can ignite without external sparks, external ignition sources at above a certain temperature. The certain temperature is called auto-ignition temperature. We have a mixture of O2 plus CH4. If we warm this cell indirectly, we can make them explode above certain temperature. The certain temperature is called auto-ignition temperature. So we have auto-ignition temperature here. So above the auto-ignition temperature, we don't need any external sources, ignition sources, to initiate the reaction. The auto-ignition temperature depends on many factors, like the concentration, the containment material, and the size of the cloud. It's very complicated function of other things. So this is the auto-ignition temperature of some hydrocarbons. Here we have methane. What is auto-ignition temperature? It's around 500, maybe 30. It's very high. C2 decreased. So C7 heptane, and octane has the auto-ignition temperature around 200 to 250. So it has some practical meaning. So do you know the difference between gasoline engines and the diesel engines? So if you understand this auto-ignition temperature, you can understand completely the difference between the gasoline and diesel engines. Adiabatic compression. Adiabatic compression is that the compression without any heat transfer with external surroundings. So if we compress the gas, suddenly the gas has no time to exchange heat with the surroundings. So the compression work resulted in the increase in the internal energy. We give work to the gas, the compression, so the gas has no time to release the energy. So the temperature of the gas increase. So usually compression means temperature increase, always. Okay, that phenomena is called adiabatic. Adiabatic. What is the meaning of adiabatic? Yeah, practical meaning insulated. Okay, insulated. The precise meaning is that no heat transfer with surroundings. So diesel engines. What is the main composition of diesel? These are diesels, C8 to C15. If we compress the mixture of air plus diesel, we can easily the temperature of diesel to around 300. Then the diesel, the temperature is higher than the auto-ignition temperature of the diesel. So the diesel explode within the cylinder, engine cylinder. And how about the gasoline? This is the main composition of gasoline. So sometimes it's very hard to reach the temperature around 300 or 350. So typically we give an external ignition source for the gasoline engines. What is the name of the small device? There is a small device to give a spark for gasoline engines. What is the name of the device? Anyway, the true function of that device is igniter. Okay? Do you know the knocking phenomena? Yeah, knocking phenomena is untimely reaction of the composition. For example, if we have a light component like C4 or C3 in diesel, Typically in real world, for the ship engines, the problem is that we have light component here, methane, the gas engine. We have the gas DFD engine is a gas engine. There's an operating mode for gas. But sometimes we have heavy component, C4. So if we compress, so the original intention is we compress the gas and we ignite, then we have an explosion that can move the cylinder. But sometimes if we have a heavy component, we compress, and before we ignite the vapor, the heavy component is above the auto ignition temperature. So there are some molecules that ignite faster than the others. Okay, it's very simple. Let's give a clap. 1, 2, 3. Would you repeat me? 1, 2, 3. 1, 2, 3. There are some guys who is more faster than most of us. So that guy gives us some kind of early ignition of the flame of the mixture. That phenomenon is called the knocking. So we have some kind of noise or kind of vibration because of the early birds. Ignition source is a major fire. It's a kind of the fire of daily life. Electrical is the number one source of ignition. Unfortunately, smoking is the second. So this is another proof that we should not smoke. There are other things. Fire, and let's distinguish fire and explosion. Fire is fire. It's a slow reaction. There are two kinds of fire. One is the more faster fire. One is deflagration. Another is detonation or explosion. So explosion is fast fire, very fast fire. Deflagration is fire where we have a kind of cloud here, mixture of methane and oxygen. Deflagration means if we ignite the gas cloud, the flame front moves very smoothly like this, about several meters per sec. Explosion means we have kind of turbulence. The turbulence can be caused by the fire, the fire itself, or if we have a congested object like this, the fire will disperse, so there can be some kind of fluid motion, turbulent flow, so that the flame can be mixed with the cloud at a very high speed. That phenomenon is called explosion. If we burn methane, the stoichiometric ratio is like this. And initial moles, 1, 2. So the total initial moles is 3 times plus nitrogen. And the final moles is also 3 times plus nitrogen. So that means the increase increase in number of molecules is not that substantial. The effect is about temperature. Initial temperature here, final temperature is very high, around 200 Celsius. So the pressure, if we apply the simple law of ideal gas, then we can have the pressure should increase about 10 times. So the explosion, the pressure increase is caused by the thermal energy, not by the increase in number of molecules. Okay? The number of molecules before or after reaction are almost the same. Because of the pressure, the energy released by the reaction and fire, the pressure should increase 10 times. What I mean is that we have one CH4, 2 mole of oxygen, and maybe 8 nitrogen. Am I right? Because the ratio of oxygen to nitrogen is 1 to 4. And if we ignite here, we have 1 CO2, 1 mole of CO2, 2 mole of water, and some energy. But the number of molecules doesn't change at all. But the energy here should be increased. The energy increase is reflected in the increase in pressure. The initial pressure 1 bar should increase to 10 bar if this system is closed. So what I mean is that the effect of pressure increase due to fire or explosion is caused by the thermal energy, not the increase in number of molecules. This is detonation. We are very familiar with detonation. Every day if we watch TV, there are many programs that give us the phenomenon of detonation or explosion. This is a kind of pressure profile. And the detonation gives pressure surge, pressure peak. Let's check two types of explosion. First one is vapor cloud explosion. Second is boiling liquid expanding wave explosion. Unconfined vapor cloud explosion means the meaning of unconfined is that the explosion takes place in an open space. Explosion, if the explosion takes place here, the explosion is bounded by the walls and windows. So this room is confined. So indoors explosion is not unconfined. Indoor explosion is confined explosion. If we don't have any walls here, but we have floor and this ceiling, and we have the explosion here, then this explosion is also confined explosion. Okay, so typically the offshore installation has this kind of structure. That we have no walls around, but we have a floor and we have a ceiling. So unconfined means explosion over there, okay, open space. So typically the phenomena concerning the vapor cloud explosion is that cloud will spread from too rich through flammable region to too thin. What I mean is here is that we have a storage tank here, and we have a leak. Then we have a cloud here. The concentration here is 100% fuel. Concentration here is maybe 0% fuel. Okay? There are some areas whose concentration is, the concentration is not like this, maybe like this. This concentration may be LEL. This concentration is UEL. So only this area can be ignited, right? So if we have a spark here, nothing happens because the concentration of the fuel is too high. So the spark should be between LEL and UEL. So the edges usually, these areas are usually ignited, and flame velocity will increase. So, and if we velocity high enough, the cloud will detonate. Okay, we have if we have a spark here, we have a flame here. If the propagation rate of this fire is slow, it is deflagration. If the spreading velocity is high, we call it explosion. So the explosion pressure is highly affected by confinement. Okay, confinement. If we in a confined area, the explosion pressure, we usually call the explosion pressure explosion overpressure, because the pressure above atmospheric pressure is important. Okay, so we usually call explosion overpressure. Overpressure. The pressure above the reference pressure. Reference pressure is 1 bar. So it's a function of confinement, cloud composition, and weather. If the weather is good, stabilized, we have more stable fire. And the vapor cloud size, the bigger the cloud is, the higher the explosion overpressure is. And the source, flash liquid, high pressure, large, low, or downward facing leak. The leak, even the leak direction can affect the size of the overpressure. Let's check here is the explosion overpressure and the typical damage. The unit is PSI. So one bar is about 15 PSI, right? So 0.8 and 7 to 8 PSI is just 0.5 bar, right? This small overpressure can cause the unreinforced brick wall fall. The brick wall without any steel bars inside can fall. So you should not be confused with the magnitude of explosion pressure and the static pressure. 0.5 bar. This is just 5 meter hydrostatic head. Okay? The brick wall will never fail with the hydrostatic pressure 5 meter. But the dynamic pressure, explosion dynamic pressure can fail the brick wall. What I mean is that the magnitude is not important. What is important is that if the overpressure is sharp or not. Let's check this. For people onshore, outdoors in the open, 0.35 bar overpressure means 15% lethality. That means 15 of 100%, 100 people can be killed if the overpressure is like this. If the overpressure is 0.5 bar, the 50 people of the 100 can be killed. As I told you, 5 meter is nothing. If we put into the water 5 meter deep, we can feel some uncomfortable, but most of us can survive if we have oxygen. But the 0.5 bar overpressure shock wave can kill half of us. So sometimes the many people are confused between the hydrostatic pressure and the overpressure, explosion overpressure. So you should understand they are totally different. There are other indicators. You can understand this one too. Vapor cloud and the TNT. World of explosive. Explosive is exploding material. Okay, explosive is dominated by, has been dominated by TNT. What is TNT? TNT is tetranitrile something. It's explosive material, popular explosive material, very popular. It has been popular. So many people try to correlate the weight of TNT to measure the explosion strength, explosion overpressure. But you should understand that 1 pound of TNT has a lower heating value. Lower heating value is just reaction energy, reaction enthalpy change of around 2000 BTU per pound. 1 pound of hydrocarbon, for example, octane, has a low reaction energy about 10 times greater than this. So a vapor cloud with 10% efficiency will expand like a similar weight of TNT. So the explosion overpressure is not a matter of energy. It's a matter of speed. Okay? The explosion overpressure we can observe, is not governed by the energy itself. Energy contained, reaction energy is important, but the speed of reaction is more important than the contained energy itself. This one is important. Boiling liquid expanding vapor explosion. So this phenomenon is very simple. We have a kind of containment. We have a fuel. Unfortunately, we have fire. If we have a fire, we try to cool down this tank. Why? First one is because of the fire, the fuel started to boil, so it will increase the pressure. So we want to cool down this one. This one is called inventory. Okay, inventory is the amount of hydrocarbon inside a segment or containment. So our first objective is to cool down, try to lower the vapor pressure. But the more important role of this spray, this is the deluge. Okay, this is the deluge, pouring water all over the equipment. The strength, the material strength of steel decreases rapidly with temperature. So we usually give a kind of factor of 3 for safety design, structural safety design. We have a margin, some margin against the design pressure, so the tank can withstand the pressure somehow above the design pressure, even though for example, the design pressure of tank is 10 bar, but the tanks are usually okay, let's spend some time here. If the tank design pressure 10 bar, the rule requirement is that the tank should withstand hydrostatic test with the pressure 1.5 times the design pressure. That means that the tank is tested to withstand the hydrostatic pressure 15 bar. So even though the pressure inside is 15 bar, the tank can contain the liquid, the vapor and liquid inside. But if the temperature of the material is increased by the fire, the strength, the yield strength of the material decreases very rapidly. So around 450 bar, we usually assume that material strength is decreased 30%. So it is very important to cool down the material of the tank. So this is the second objectives of the deluge system. Anyway, we have fire. The fire in offshore is very strong. Considering the speed of the leak, and we have a jet fire, the leak just after the hole, leak point, is soaring. So the speed of jet is tens of meter per sec, and the length is tens of meter. So even though we pour some water through deluge system, the effectiveness of the deluge system is not that substantial. So it just delay the explosion, cannot prevent the explosion. So ultimately, the tank will lose the strength, and ultimately the vapor will explode the tank itself. Then this liquid at high pressure will release a lot of vapor because it was in a high pressure. The tank is ruptured and the pressure is decreased, and it can generate a lot of vapor. The vapor now is ignited and make a big explosion like this. So I think most of you are very familiar with this phenomenon on a daily TV programs. Most cars are exploded like this. But you should understand that the gasoline from the car should evaporate, okay, to make explosion. So some kind of things like that, if the car crashes with the building, there is explosion. Those kind of things makes no sense. Okay, the liquid should vaporize. So we need some time for the gasoline to vaporize and make a cloud whose concentration should be between LEL and UEL. Then there is some ignition source. Then the cloud can explode. Okay, that's all I prepared today. Any questions?